Right. Hi. Today we're going to talk about knot coloring and how that's going to help us distinguish between two different knots. And so let me give you a quick definition. A knot is an embedding of a circle S1 into R3, 3D space. And so maybe I'll just draw some examples. Uh, well, the simplest knot you can think of is just a circle, and we call that the trivial knot. And another knot that you might also be familiar with is looks like that, and it's called the trefoil knot. So these are just two examples of knots. Something that will be helpful for us today is to just give them some names. So the components of these knots some names. So I could call this portion over here. I'm just going to highlight that. We can call that a strand. So it's well, a line segment on a knot, we'll just call it a strand. And so the trefoil knot has 3 strands, while the trivial knot has just 1 strand. And these intersection points, we can just call them crossing points. Yeah, so that's just some example of a knot and knots. And a good question you can ask is how well, is the trefoil knot different from the trivial knot? Could we deform the trefoil knot so that it becomes the trivial knot without cutting anything or without passing the trefoil knot through itself? How do we know that they're not secretly the same? And so this is where knot coloring is going to come in and help us answer this question. But before that, well, I'll introduce this thing called Reidemeister moves. And so Reidemeister had this insight in the 1930s that well, any two, you could do 3 things to a knot. And you could do 3 things. You can move a knot in 3 fundamental ways. The first one is called a twist. So, well, imagine a piece of strand, and you could deform it as such with a twist. And you would get the equivalent knot just by deforming. Or maybe you had a knot and you had 2 strands that are close to each other. You could just poke one over the other. And so the result will look something like that. Or you could slide it. So you have a strand and it's going to slide over a crossing point. And so the result would look something like that. And so these are 3 ways that you could move a knot to the other, and that shows that they're going to be equivalent because you're not cutting anything and or passing it through itself. And so important relation to note is that 2 knots related by a sequence of these Reidemeister moves, and I'll just abbreviate them as R moves. If they're related by sequence of Reidemeister moves, then the 2 knots are equivalent. And Reidemeister also showed that the converse is true. And so if 2 knots are equivalent, there's a way to deform one to the other by using a sequence of these Reidemeister moves. And so that tells us how 2 knots could be the same by just deforming them. But we want to but we also want to know, okay, how can you tell them apart? And so that's where knot coloring comes in. And that would give us a way to tell them apart. So a knot, well, we're specifically going to think about tricolorability. And so a knot is tricolorable if each strand can be colored using 3 colors, such that in the entire knot, at least 2 colors have to be used. And also, secondly, at any crossing point, the colors of the strands have to be either all the same or all different. So we have 2 pictures on the right here that kind of illustrate that. They have to be all the same or all different. So let's just explore a tricolorability on the 2 knots that we talked about before. So the trivial knot, this turns out not being tricolorable because if we put any color on the strand, it would only have to be 1 color, and that violates the first rule. Whereas the trefoil knot is tricolorable by this coloring. And so as you can see, at least 2 colors are used. And at every crossing point, either the colors are all the same or all different. And so, yeah, and so we have that the trefoil knot is tricolorable. And so tricolorability is going to be helping us to distinguish between knots, because it turns out that the Reiter-Meister moves preserve tricolorability. And so that means if we deform the trefoil knot in any way using the Reiter-Meister moves, the result has to be tricolorable, because Reiter-Meister moves preserve the property of being tricolorable. And so that means you couldn't have got to the trivial knot, and so therefore they could not be equivalent. And maybe just to explain why the Reiter-Meister moves preserve tricolorability, let's just run through a couple of these examples. So imagine we had a twist on some local region of the knot. Let's just say it was all red to begin with. So if we apply a twist to it, okay, let's notice that the top and the bottom of this resultant strand is still red. So we're trying to preserve the rest of the coloring. And all we can do is just to, well, paint it by the same color. And we find that, okay, we're still tricolorable because the rest of the knot is tricolorable. For the second one, poke, okay, keeping the rest of the knot of the same color, I could do red over here, blue, but make one small change, and that is to make the middle green. And we have still a tricolorable local region even after applying a poke. For a slide, and let me color this in. But I just want to show that the local regions, when you apply Reiter-Meister moves, maintain the tricolorability. And so we can see that over here. And so yes, so important thing to note is that Reiter-Meister moves preserve tricolorability. And so if one knot is not tricolorable and one knot is, we can know that they are different. But one important thing is that we cannot tell if they're the same. That's not necessarily true. And Alexander will take us through a couple examples to really explore that.
Yeah, so I wanted to start off with the figure 8 knot, also referred to as the 4-1 knot, because it has 4 crossings, and the 1 is just an arbitrary index for all knots with 4 crossings. Okay, so let's see if it's different from the trefoil knot. So is there some way that we could apply the Reiter-Meister moves to the trefoil to get the figure 8? Okay, well, let's start by coloring this left strand red without loss of generality. And now for this right strand over here, we could also color it red, but I will leave that to the viewer to check that the whole knot will become red. We'll be forced to color the whole knot red. That will violate rule 1, and so that's not a path that we can take. So let's color it blue instead. Okay. Well, once we choose blue for that right strand, well, based on this intersection here, this strand must be green. Otherwise, we violate one of the rules. Okay, and now we sort of run into a problem. Based on this intersection, the top strand has to be red, but based on this crossing point, the top strand has to be green. And essentially, this shows that there's just no way to pick a color for the top strand, and there's no way to color the figure 8 knot. Well, just as before, this tells us that these two knots cannot be equivalent, because the Reiter-Meister moves would allow us to take the coloring for the trefoil and produce a coloring for the figure 8 knot if they were equivalent. Okay. Well, let's sort of see how powerful this tool is. Can we figure anything out about the trefoil and the 6-1 knot, the knot with 6 crossings? Okay, well, it's not the only knot. There's also a 6-2 and a 6-3, but let's look at this one. So if we color this left strand red, and then let's color this next strand right here blue. Okay, again, if we chose it to be red, we would end up violating rule 1. Okay, and from this moment on, our hand is forced. So based on that intersection, this strand has to be green. Then based on this intersection, this strand has to be red. And then based on the next intersection, this strand has to be blue. And finally, this last strand in the middle, well, if we look at all the intersection points, for each of those, it agrees. It has to be green. So this knot is three colorable. Nice. But that actually doesn't tell us anything about the trefoil, or if the trefoil can be deformed through the Reitermeister moves to the 6-1 knot. We don't know if these are fundamentally different. So this is where we can use a more powerful tool, p-colorability. Okay, so this is a fairly natural generalization of three colorability. So instead of choosing three colors and labeling each strand with one of these colors, we're going to instead use numbers from 0 to p-1, and these will be our colors in quotes. Okay, so now that we've assigned each strand a label from 0 to p-1, what are the rules for a p-colorability? Well, the first rule stays the same. We have to use at least two colors. And the second rule is that at any given crossing point, like here on the right, we want the color of the left strand plus the color of the right strand to be equal to 2 times the color of the over strand, the strand which sort of goes over the strand that's going underneath it. Okay, and then one can check that in the case that p equals 3, this is equivalent to the rule we had for three colorability, that they're all the same or all different. Okay, well, that's the case of p equals 3. What about other values of p? Well, p equals 1, that violates rule 1. That doesn't necessarily make sense. P equals 2, it turns out that no knot is too colorable. So we don't really care about those values. And now for values of p greater than or equal to 3, well, it turns out that p colorability is uniquely determined by the divisors of p. So 15 colorability is determined by 3 and 5 colorability. So in fact, we only care about p in practice when p is a prime. Okay, cool. So let's look at maybe an example of how this coloring might look. So here on the left, we have an overstrand of 1, and the two understrands are labeled 0 and 2. So we can check rule 2. We have 0 plus 2 minus 2 times the overstrand, which is 1. And oh, this is equal to 0, which is exactly what we wanted. So this is a valid way to 5-color a single crossing point. All right. Does this solve our problem? Can we now say that the 6-1 knot is different? Okay, well, let's sort of fill out this table. So we know that the 3-1 knot, the trefoil, it is 3 colorable, and we know that 6-1 knot is 3 colorable. We know that the figure 8 is not. Okay, and now if we look at 5 colorability, well, it turns out that the trefoil and the figure 8 are both 5 colorable. But if you were to, go through and check all the cases, the 6-1 knot is not 5 colorable. So what does this tell us? Well, before we thought that maybe the trefoil and the 6-1 knot were the same, but now looking at 5 colorability, we know that they have to be different. And this actually begs a more general rule to distinguish any two knots. We can take any two knots and we can look at p colorability for larger and larger prime p, and this will tell us exactly if these two knots are the same. So if the two knots agree for all p, then we know they're the same. And if they disagree for any p, as in one of them is p colorable and one of them is not, then we know the two knots are different. So now we have a general way to distinguish between any two knots using p coloring.